friction that we could potentially do a little bit more with, because we know that in general, the magnitude of the frictional force is going to be equal to something about the surfaces, mu, which tells us the coefficient of friction, the stickiness between, in this case, the skis and the snow, times the normal force, the size of the force pushing those two surfaces together. So this may or may not come in handy. We don't know. We've got some unknowns that we could work with there. And then in the y dimension, we are going to start with Newton's second law again. The sum of the forces in the y dimension will equal this object's mass times its acceleration in the y dimension. We have two forces, one real one and one component. Our normal force is in the positive direction. We'll add that to the perpendicular component of the gravitational force, which is in the negative direction, negative mg cosine theta. That will be equal to this object's mass times its perpendicular acceleration. In this particular problem, we already talked about the fact that this skier could be accelerating up off the snow. The skier could also be accelerating down into the snow. But it's most likely in this particular scenario that there isn't any perpendicular acceleration. So this might be, in this particular case, might be 0. And typically we'll either be told that or we can assume it. If you had a problem where it was like a skier is skiing down a hill, blah, 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 blah. But as soon as you read skiing down the hill, you can assume that there is no acceleration in this perpendicular dimension. Which means, if that's the case, then these two forces, the normal force and mg cosine theta, have to be equal and opposite. And that's where, if you get on Google and you type in what's the formula for the normal force, you're going to get normal force equals mg cosine theta. Why is that? Because an object on a sloped surface that isn't accelerating perpendicularly to the surface and isn't experiencing any other forces perpendicular to the surface will have a normal force equal to mg cosine theta. And that's relatively common, but it's not always true. Here's some other things that we can do. We've got a normal force here, and that is the same as this normal force. There's a variable that connects our x and y dimensions in this case. That's not always going to be true, but in this case it is. The friction of this object is dependent on the normal force. The normal force is in our y dimension, friction is in our x dimension, so we have a connection there. We also have a connection with our accelerations and kinematics. If the sum of the forces is constant, then the accelerations will be constant. And if the accelerations are constant, we can use our kinematic equations. So in a problem like this, if they're talking about skis for 11 seconds, starts at rest, and we want to know how fast will it be going at the end of the 11 seconds, then we're going to take all the stuff that we get from this and use that in our kinematic equations, where the initial velocity is 0, initial, like the difference in time is such and such, like figure all that stuff out based on the assumption that our forces are staying constant, which means our acceleration is also staying constant. Okay? So what I told you before is that this, for some of you, is just too much, and that's okay. Fine if this is too much. Just recognize that this ultimately is where we're going. You'll all be needing to work with stuff like this. We're going to do homework problems like this. We're going to do labs like this. We're going to start today with, it's not a formal lab, but it's just something to think about, and we'll keep doing this on Thursday as well. So if we have a supercard with, like the supercard itself has a mass of about 0.3 newtons, or sorry, 0.3 kilograms. And we put two bars on it, two of those big metal bars. Each of those has a mass of about 0.5 kilograms. So in total, thank you. So in total, this mass right here would be about 1.3 kilograms. And we want it to accelerate to the right in this drawing at a rate of about 0.8 meters per second squared. Then we want to know two things. One is, how hard will we need to pull in the direction of its acceleration? And how much mass would we need to hang over a pulley in order to get it to accelerate at that rate? And this is a little tricky because what many of you will kind of arrive at is that, well, if we know this pulling force, then we can figure out the weight here, and then we can use that to figure out the mass. But it's not as easy as just saying the pulling force and the weight have to be the same, because that won't work. And I'm not going to go into any more details about that right now, because what I want you to do is tackle the first part, and I want you to use the process. So you're going to make a drawing, you're going to make free body diagrams. You won't have to worry about breaking forces into components because we're keeping things simple for this one. Everything is either perfectly horizontal or perfectly vertical. And we'll start with trying to figure out the pulling force needed to accelerate it. From there, we'll move to the more complicated problem of trying to figure out how much mass we need to hang off of the edge. Before you do any of that, you should go take a well-deserved break. I'm going to shut the recording off. Let me know if you have any questions, and you have the rest of the period to try to tackle these.